I write a compiler for a small imperative programming language. The compiler is written in multiple stages, where each stage can do a few more things than the previous stage. And that also means the compiler is written in itself, so it is self-hosted, but it isn't completely implemented, meaning that I write the compiler in the language itself, but I cannot use all the features because not everything is implemented, and there are still a lot of things that should be done. For example, error checking is almost missing. I use Rake as a task runner, so it's just for convenience. So I can write tasks then that I can execute, and I use Ninja to build the compiler itself. Okay, we need to remove the old build file and generate it again. Okay. The last stage, the current stage that I'm working on is 21. We do not have modules yet, so all the stuff is basically in a single file. And now it compiles the current stage with the previous stage, and then with itself, and do some validation. And I think that we can go to the source code itself. I'm working on assignments, and on assignments not for basic types, but for aggregate types like records or arrays. So assignments, if I assign two local variables to each other, so Elna location is a record with two basic fields, line and column, and then I define here x and y, and I assign values to the y variable and assign it to x, and then print everything. If I compile it, I print it into a comment in the generated assembly, and if I compile it, then the output is 1313. So the first 13 is from the x variable, and the second from the y variable. So this works as expected. The one thing that won't work, because it will generate different instruction, is assignment to fields of a record, and we will use a different variable. For example, this Elna position is good because it contains two Elna location fields. So we define a new variable, let us call it just z, I suppose, and its type is Elna position. We still assign values to the y variable, but instead of x we will use this Elna position. This is, for example, z start location, and then we print it. So the field access already works. The one thing that probably doesn't work is the assignment to a field, and assignment to a simple field works as well. So assignment to an aggregate field won't probably work. So we print here, for example, the start location line, and the same in this case. And now we switch to the assembly again and try to compile it. And the output that we actually get, so we get 1 and 3 for Y line and column, but some random garbage for these two variables. Let us check. So I currently work on the stage 21, and the stage 22 is just the test stage currently, and it is a copy of the stage 21. To make the updates to the stage a bit easier, I have a rake task that copies the stage 21 into 22 and adds some test code. This is actually how I test the compiler, so we just adjust the code here. I think that we do not need this X at all, so we can just rename or change the type of this X variable to the position and the position. And we do not need to allocate it yet, and then we set the field, and here we say that we want assign the start location of the X variable, and then we want print it here, start location and start location. Then I have a rake task convert, which copies stage 21 to 22 and adds this code here, and then I can compile everything once again and check that it works. So if I reload this here, then we have these two variables, elna position and elna location, added. I think the alignment here is actually wrong. It should be one tap, I suppose. The indentation seems to be off. So I already called try convert and compilation. Okay, that looks fine now. And then we can go back to the stage 21, and actually if I look into the generation for the assignment statement, then I check here whether our type, whether the left side of the assignment is the reference pointer. The reference pointer is the reference pointer, so it would be something like, I should switch to the stage 22 here. Put stage 22. The reference pointer would be actually something like x is 3. So x is here the reference pointer. In the case of the field access, I think that we generate this copy to offset instruction because we copy it to an sub-object, and we are going to check whether it is right by printing both arguments. So I add a comment like debug here and just print a comment into the generated assembly, and we will print probably the left side of the assignment, the operand kind, and its name. So assignment operand is the right side. The left side of the assignment is actually this stuff here, I think. And the length and the value should be swapped in this case for the printf format. Okay, where will be the generated code? The generated code will be in the boot version of the stage 22. And here we have, for example, left x and 2 times y. So these 2 times are y on the left side, and this 1 time this is x. So this is actually fine. So we basically generate a copy to offset instruction, and let us also print the second operand, so the assignment, the first actually. And here as well we need to swap these 2 things. In the generated assembly, now we have left x and right y, which is actually correct. And we also will have the offset here, which is probably, which will be 0 because it is the start location. But well, let us go to the copy to offset function. So here we have the next pass of the compiler, which converts this 3 address code instruction to the assembly. And probably if I look at the function itself, it should actually call mmcpi to copy the memory, but it doesn't. And actually this function should be pretty similar pretty similar to the copy function or store function, I'm not sure. Copy to offset. Let us look probably at the copy function, so add title copy. And here we have source and target, and here we generate instructions to get the first operand, and then we generate a store instruction. In the case of copy, we do not generate a store instruction, but we actually just generate a move instruction from one pseudo-register to another, and in this case we generate an MCPI call. So this is probably more similar to the tail store function. But anyway, we will need to get the type of the operand, so we will define a new variable, pseudo symbol. And in this case, we are interested in the left-hand side. Which is X in our case, but where does it go? So there's C assignment, and here we set the assignment, so the source is the first argument, but we are interested actually in the second one, I think, because it is the destination, and the last argument, the last operand is the actual offset. So here we generate a new variable, and we'll add the address of the second instruction, so from the target, and we append the instruction. Okay, let us just copy it from here. So we look up the first variable, copy to offset, this actually doesn't matter, I think. So we can check the first argument. In our case it will be X, and it will be a pseudomem. So then we can check whether it has the type that I need. So I want just to ensure that the value is always given, so we print a pointer here. Oh, it is 0 sometimes. It is nil sometimes. Interesting. For which values actually? So sudo the second instruction can of course be a constant. Okay, whatever. So we do the same as we did for the store instruction. First we check whether sudo symbol is nil or not, and only if it is not, then we check whether what is actually its type, and if its type is a byte array, then we want to know it and print, for example, again the same thing, be in the name of the first operand. So here we put length as the first argument and value as the second one, and compile this thing. And we have one single output with y, so this is the correct place. Actually, we can put everything else, or at least everything after this operand value function, we can put it into else. So we move it in here, and or if the type doesn't match, then the handling remains. So what I actually will do, I just set the sudo symbol to nil here again, and then I check it for nil, and only if the sudo symbol is not set, then we do this generation for normal pseudo variables, not for memory regions. So okay, and now we only need to generate MMCPI instruction. I think first we need to set the first two registers, A0 and A1. A0 is the target. Actually, we can do it for the start location just for testing. We can do the same as for copy offset, so just ignore offset for start location, it will work. And then in the next step we add the offset. So what do we actually do? The first instruction is a move instruction, and it copies operand 2 as target of the copying, which is actually correct. So this actually should be fine. But here is some error. can just remove this line for now, so a semicolon is missing. And this compiles now. And now we can set A1. So we load the address of the first operand. This RTL operand is actually this thing here, so it should be called source operand and not RTL operand, but otherwise it's just an operand variable, yeah. So we will call it source operand. And after that we can generate the remaining arguments and a memcpi call. But this does nothing, of course. But now we have actually a call to memcpi. And we already can handle the second case. So the problem is that we need to add the address of this thing to handle it properly. But at least it now works. So actually this is a similar handling as the copy instruction, but we need to add an offset to this 0 So the assignment to the first field works. Now we want to change. It works because we assign to the start location, and start location has the offset 0 because it is the first field in the record. But if we use the end location here, we will get actually the same result, and I probably shouldn't change this stage. Okay, for testing we can work here. And it compiles, and it still prints 1, 3, because even if we use end location, we ignore the offset. And actually, if I print end location here, then we will get a problem. Exactly, so we still have garbage as the output, and I will modify the rake file once again, so we use end location here. The editor just continues to replace tabs with spaces. So the offset is actually the third operand, I think, and the easy thing to do is just to generate an additional add instruction. So RISC-V has an add immediate instruction. Our target register is A0, and our second operand is A0 as well. And then we only need the, I think we need an additional register, can it be? So if I generate an AD, I set the third operand to an immediate. Okay, let us do here the same. And the offset value, this is copy. This is copy to offset. This is copy to offset. And it sets the third operand to a constant, and this value is actually the value of the actual offset. So in this case we have an immediate here. These two operands, these two arguments will be 0, it should be fine, but this one is actually a TIC instruction, operands 3, and it is the value of the third operand, and we need to append this instruction to the instruction list. And this one works as well, so now we have a correct value here. So this is actually done. We can go to the stage 22, I suppose, and test a few more cases. Another interesting case would be, of course, to test whether it works with, actually it should work with things like pointers. If I have a pointer inside a record, let us define a type just for testing. For example, let us call it elna_x, and it will be a record, and it only field, we add two fields to it as well, and they won't be the location itself but two pointers. If I now basically replace this x type with elna_x, then I should allocate some memory for the end location. This was elna location, I think. And then I should dereference it before I can assign a value, and if I print it, then I should dereference the field as well. The referencing works. The only thing that probably doesn't work is really only the assignment. So let us try to compile it. Yeah, it generates invalid instructions. I think the code itself is fine. So we have this Elna X record. It has start and end location, and these are 2 pointers. And I allocate the end location. And assign the value to it. And the second operand of the add instruction is actually an X. If I remove this line, then we still have this problem. So this is a different thing probably. Let us define a variable z, because this thing is actually a different problem, I think. and we will try to use it as an intermediate value, and we assign this x and location to this variable. Then we can say that we want to reference the z and print the count, because I want to see at least whether the assignment itself works. And it does, as it seems. So this thing is actually works the assignment as expected, but we have a different problem that is not the topic for this time, I think. I'm not sure where this add instruction is coming from. So probably because it is an argument to the function. They are passed a bit differently, and the code generation is probably not complete. So the case that doesn't work is and location is actually this one. And the problematic thing is the printf itself. So even if I remove everything, it still generates the wrong code. And we write something from x6 into x5. x5 is probably t0. 1, 2, 3, 4, 5. Yes, x5 is t0. T1 is also used pretty often. So that I can see the error message, we have T1 as the third argument to the add instruction. Here we have stop word instruction. Here we have load word, load address, store word, load address, store word. Okay, and here we go back. I think that this thing will actually work if I, for example, assign it to a variable. So if I, for example, say that this z is a word, we need then two z variables. Let us use t and u. And if I assign the column or the line to the t and the column to u, then it could actually compile, but it doesn't. So no, it is a more general problem. I kind of wonder why do I see it now for the first time, because I actually use stuff like this, so pointers inside of records. In my allocator pass alloc, I should actually have allocation for the add instruction, I think. But actually the instruction itself is pretty strange. So it generates x plus something. But why? Oh, of course, x plus offset. But it should be the address of x and not x itself. So no, the code generation is not correct here. So just it isn't just an allocation problem. In this case, it probably generates something like copy from offset. In this case, I generate load word instruction. Can we go back to the copy to offset? I just thought of one thing. This LNTL, so this target operand it is used in this case, but it isn't used in this case. If we copy an aggregate, I can replace the so what does actually this function do? LNTL operand address, so it loads address of a value. And it always generates a load address instruction. But its target is different. Yeah, I do not need this instruction here, and I do not need the target operand here. So basically the problem is that I want to move this thing to this branch. But I am on the wrong stage. Let us overwrite this stage once again. And we go to the stage 21 and to the usage of this function in this case. And we move all of this stuff to this branch. And now we test it again. So here we have the correct result. This is fine. Okay, and that looks fine. We have here this printf. We do not need it anymore. We can remove it. And now we go back to the problem with the code generation for the pointers inside of the records. And as an example, we will use an existing type instead of defining a new one. For example, I have an ELNA type field here, I think. So this type here, and it has field type member, and this field type is a pointer to an aggregate, which is exactly the case that we have. So basically we will replace X with ELNA type and Y with ELNA type field. Then we will use the size field of the ELNA type for the testing. So it is just a word, so basically a number. We assign it value 3. Then we need to allocate memory for the field type. And finally we want assign, and this is Y, and we want to reference the field, the aggregate, and assign X to it. After that, the only thing that we can actually print is Y field type and size. This is actually everything we care, and it covers all the problematic cases. So now we can say array convert to update the latest stage, and now we can compile. And we have this error. I actually already found what is the problem. There is a problem in the 3 address code generation, and basically if I have a reference expression, I generate the code for the body of this reference expression. So basically it is called designate in this case, and I save the result in the operand. In the case of the field access, this result will be Y plus some offset for the field type, and then I use the same variable, so the same Y variable with some offset. I use it to save the referenced thing, so to dereference the pointer. Basically, I just overwrite the context of content of some memory with an offset from Y. To make this short, I only can pass operand further as this if this is a plain object and not a reference expression or a field access. In the case if this is a field access, we first need to save the result of field access in intermediate variable and then pass it to the caller the name of this intermediate variable, so that this intermediate variable can be used in further calculations. So I just define a new variable, intermediate, and let us see operand, and then I allocate. I actually want to copy the contents of the operand into this variable, so I call memcpi and copy operand into it with the size of the lnatic operand. I need to copy the operand, so I have the result of this designator, so of the body of the reference expression, so that I save it in this intermediate variable, and then I can override the operand with a new variable, lnatic make variable, I think. lnatic make variable, it gets the operand as its first value, and then the symbol table, and then the variable type. The variable type will be a word type since it is a pointer. And actually the only thing, so operand is returned here, so we need to write it into the operand. But the third argument is the result. The first one should be then written with the intermediate. And now we can compile it. Now we have another problem somewhere. lnatic make variable. Of course, operand is already a pointer. And now we have the same error, but this time into the validation stage of stage 22. So at least this stage compiles already, yet now we can copy our changes into the 22nd stage, and we can compile it once again. And finally we can look into the assembly. Valid stage 22 CLS, and we have 3 here. 3 is exactly the result that we expect. So basically we write 3 into here, and then we assign this this x aggregate to the field type pointer, and then we print it from the filter from the y variable. So this is then fixed. We have actually the same situation also here. So the same, if if the designator is just a variable, then we can override the value in this variable with the reference value, and we the value in this variable. So we if operand from the designator is a variable, it is dangerous since it can override a variable with a temporary value. So I think that we actually want to do the same here as well. And in this case, it's actually the same. The first operand would be this intermediate thing, and here too. Now we can test it once again. And we can look into the assembly. The assembly looks fine still. And now we can just remove some debug code. I think these were only these two printf statements. They can go. Convert. Okay, yes, that looks fine now. And I suppose that this is for today. So I still have one case that won't probably work, and this case is assigning of field access expressions to some variable, to some memory. I think we did only the other way around. So we did copy to offset. Exactly, we did copy to offset, so assigning to a field, but we haven't implemented assigning from the field to some memory if the field is an aggregate. Unfortunately, I wasn't able to do it now because of discovering a different bug with the code generation that we fixed. So the assigning of record fields of aggregate types will be done later then, and I'm going to finish this video here.